Here we are going to see the generation of ASK and detection of ASK. We already know the equation of ASK, S of t as A into cos 2 pi fct into B of t. B of t is my input binary data. It is product modulated. So product modulator, and this is our high frequency cosine wave, and it is generated by an oscillator. This is my oscillator. I am writing as A into cos 2 pi fct. This is our carrier, and the product modulated output will be S of t, and this is our ASK signal. This ASK signal is now transmitted either wireless or wired. We are assuming channel to be noiseless and everything to be ideal. This ASK signal transmitted is received by a receiver. Now the receiver job is to detect the ASK. Detection of ASK. The receiver can use two methods. Either it can use a coherent detection. The receiver can use two methods for detection. Either it can use coherent detection of ASK, or it can use non-coherent detection of ASK. By the name itself, in coherent detection, there should be something common. Common something between transmitter and receiver. If it is coherent, common. The common quantity is the frequency. In coherent detection of ASK, the frequency and phase should be same as what was used for the generation of the ASK. Like which carrier frequency you have used, it should be same here for detection also. So hence we can say this requires a synchronized frequency and phase also, but the phase we are neglecting here, so for simplicity purposes I will write Fc and 2 pi cos, and we are assuming amplitude to be same also. This can change, but the main thing is this should be same. Now the coherent block diagram I will draw here. The received S of t signal, that is ASK signal, is passed to a product modulator again, and since I have already mentioned we are going to use the same frequency which we used for generation, the same carrier frequency we will use here. So again we will have an oscillator that is going to produce the same frequency component. Since for simplicity I have assumed the amplitude to be same, so A into cos 2 pi fcd. The output is represented as V of t. This output is passed to an integrator, which is going to integrate it. It is going to sum up all the data. Then this integration is going to perform for 1 bit duration, that is TB. TB was our time period of a bit. So this is going to integrate for 1 bit time period. And the output of this, let me say Y, is passed to a detection device. The duty of the detection device is to find whether the bit was 1 or 0 by using a threshold value. Let me say lambda. This threshold value acts as a guide. If the output is greater than equal to lambda, it is going to assign some value. If it is less than lambda, then it is going to assign some value. We'll see this, what are the values. Now let me write the equation what we get after the product modulation of this S of t and this, our oscillator. V of t will be simply S of t into the oscillator E into cos 2 pi fct. S of t is our ASK signal, which was A into cos 2 pi fct. B of t, A cos 2 pi fct. This we will get as A square cos square 2 pi fct B of t. By using half angle formula, we are going to bring the square cosine into linear. So we can write V of t as A square by 2 B of t plus A square by 2 B of t cos 4 pi fct. Next thing is this V of t is passed to an integrator, which is going to integrate for 1 bit time period. So we'll write here y equal to 0 to tb V of t dt. This will be 0 to tb A square by 2 B of t plus A square by 2 B of t cos 4 pi fct dt. Before performing the integral, we will see something here. This integral is going to perform with respect to t, but there is an interesting thing to see, that is, there is a relationship between the carrier frequency and the bit time period. And what it is the fc is given as n times the bit rate 1 upon tb, and 1 upon tb was our bit rate, so n into rb, where n belongs to an integer, and this n is an integer, and we should take some higher values like 10 and 20, not 1 and 2. Why so? We will see from here. This was the result which we got when we did the Fourier transform of our ASK equation. This was the carrier frequency, and this will be fc plus 1 by tb, and like this. This we got the result, and this was fc minus 1 upon tb. And here we are saying that fc is n times rb, and 1 upon tb is rb. fc plus rb, fc and fc minus rb. Here also this is minus fc plus rb minus fc, and this is minus fc minus rb. This I did in the first part, you can check that video. Now if I am saying that fc is n times rb, and if I take the value as n equal to 1, then what will happen? If n is equal to 1, then this is fc and this is fc plus rb. Then fc is equal to rb, then this fc minus fc is equal to rb, so this will go to 0, right? Since fc is equal to rb, and I will plot it here. This comes to 0. Now this is fc, okay, and this fc, this becomes twice, this becomes twice fc, and our graph will look like this, our sink. The same story goes here also. Minus fc plus fc, that is 0, right? So this is like this. This will be minus 2 fc. Now what we can see here is there is an interference, right? To avoid this interference, we take a larger n value so that these loops are found far. We have seen now why we take larger values of n. Now the cosine being an integral multiple of an integer, right? This will be an integer multiple of this, so this part will become 0, as because the cosine is 0 for integral of 2 pi, right? Therefore we are left with only this part, that is 0 to tb is square by 2 b of t dt. If our b of t is 1, like it will be 1 and 0, so for bit 1 we will get a square by 2. Since it is constant, it will come out of the integral, and this will be square by tv. For b of t, when it is 0, the integral will become 0. This is for b of t when it is 1, then this is for b equal to 0. The integral will become 0. We got the two values of this. These are the two values of y. To find the threshold, we take the mean of these values. So lambda will be simply the mean of this square by 2 tb plus 0 by 2, and we will get a square by 4 tb. This is our mean, and this is our threshold. So we have seen the threshold value. Now if it is greater than this, if our y is greater than this, then we will assign 1. If it is less, then we will assign 0, and this way we are able to detect the signal.